This module is about software development, and this is sort of the vanilla software development lecture. We're going to keep it real short. We're going to look at some different models, some of which you'll be familiar with, maybe all of which you're familiar with, but just we have to do this because so much of what we do in modeling and simulation is software. It just is. It's very IT based. It's why we focused on IT so much in this course. Is because so much of what we want to do involves writing code, and maybe not us writing code, and maybe having contractors writing code, but writing requirements and making sure that we get what we're asking for and that we plan ahead, hopefully understanding that because software is different from tangible hardware sorts of procurements, you got to treat it differently. So that's going to peek out a little bit in this lecture, a lot more when we get to system architecture. The system development life cycle is typically divided into 7 phases. You'll have the initiation phase where there's an opportunity to add, improve, correct a system. There's planning, the most critical step in completing development, acquisition, and maintenance projects. You want to be very careful to coordinate activities and manage project risks effectively at this point. Then there's design. You want to convert information, functional and network requirements. You want to do UML diagrams and things like that so you thoroughly understand. It's not vague at this point. You want to use prototypes if you can. When you get to development, I like to think that when you get to development, you should have somebody fresh out of school who has nothing but coding skills, not design skills, but coding skills, who can do exactly what you just told them to do. You don't want those people making design decisions. You want them developing what has been designed. So that's sort of something you can think about for what you want to come out of the design phase. Then testing. Once it's been developed, I have to assure that the accuracy of the code. We talked about IA earlier. Information assurance tests are going to come in here, and then finally, you think, well, isn't implementation and development the same thing? They're not. Development is writing the code and then testing it. Implementing is actually deploying it, getting it out there, having real people use it because it's thoroughly been tested. And then you want to maintain it throughout its life cycle. There's really, some people would say there's lots and lots of different software development models. I'm going to really talk about only 3 here today. Almost everybody has heard of the waterfall model, and it's simple, but it has some baggage. It has some clear limitations. What really replaced it mostly was the spiral model, which has some definite advantages. And we're hearing more about this V model. So we'll look at them. You'll see that the very same parts. We just talked about all the 7 phases. The 7 phases are going to be present in all 3 of these. They're going to be present in any model that you're going to see. What we're not going to talk about today that might be relevant to you would be like extreme development models or agile development models, which there's some interesting characteristics of those as well. And they're not necessarily mutually, I don't put those in here because they're not really mutually exclusive to these models. You could do an agile development model and try and implement it in a spiral, for example. So the waterfall, you look at the different pieces here, and it's waterfall because everything is trickled down. You complete the steps in a specified order. You define all your requirements up front. You have comprehensive reviews as the gates between the different steps. You complete your entire design before you code, and you elaborate on the design by extensive documentation, et cetera, et cetera. And there's a feedback mechanism going back up, so you can iterate back around. But one of the reasons why you'll see that the spiral method seems to be preferable to the waterfall method is that it inherently assumes multiple iterations, whereas the waterfall does not. The waterfall, some folks would say that the waterfall in a perfect form would mean that you do every step exactly once and perfectly. And in practice, that never happens. You're going to iterate lots and lots of times. The spiral method pretty much assumes something that's closer to reality. So here's the spiral method, and you can see different words here, but the gist of it is that you've got all the same phases. All the things that you saw on the steps on the waterfall are sort of now in pie slices on the radials in the spiral. And what the spiral is basically showing is that we're going to iterate through these different phases multiple times. We know we're going to do it multiple times. This tends to be favored for large, expensive, or complicated projects. And one of the other things that you'll find, the reason why government programs really prefer something like a spiral, is that since we tend to have development teams that are disparate, so you'll have different companies, you'll have primes and subs, you'll have government organizations participating along with private sector and industry, and you got an integrator who's got to pull all this stuff together. The spiral allows you to have insertion points. So you'll say, at this point on the spiral is where I accept insertions of new pieces from all of my performers. So if I'm at the Naval Postgraduate School and I'm one of the performers on this big software program, when you get to the insertion point and I've got a cool thing that I got from a student thesis that I'm going to insert into the program here, that's my point. I stick it in there. If I miss that wicket, I don't get an opportunity to put it into the system until an entire iteration comes back around, and now we're back to the insertion again, and now I can put it in. So you don't just take things haphazardly whenever you want to. There's an actual point in here for technology insertion. And the last one I'm going to show you here is the V model, which arguably is competing with the spiral model as a preferable way of doing software development. You loosely think of this in terms of definition down the left side of the V, implementation across the bottom, test and evaluation on the vertical going back up. And you'll notice all the feedback loops going back and forth. So as you're doing test cases, you're kicking back across from test and evaluation back into steps like architectural design, detailed design, design specification documents, et cetera, et cetera. So you can go through that. This is where you sort of simulate. It doesn't assume that you have to go through all the steps on every iteration, which is why some people think it's preferable to the spiral model. It allows you to go directly from an integration test back into whatever step you want to go into over on the definition side, because you just realize that something you thought was defined isn't as defined as well as you should be. You're going to clean it up. You're going to go back down into implementation, fix it, test it again. And eventually you iterate towards something that is solid and is now ready for full product testing. I wanted to say a little something about agile methods before we move on. First of all, it's not incompatible with the models that you just saw. So you can do a V model or a spiral model and still follow an agile development process. But the gist of agile methods, just in a nutshell, is very small teams. You don't have like a manager that has a whole bunch of programmers underneath them. You break up into teams of 2 or maybe 3 people. Very often it's 2. So you get 2 pairs of eyes on every line of code. There's something that's you often refer to as a scrum at the beginning of the day. Everybody huddles and they all talk about, okay, what's everybody doing? What problems are you having? How is that module going to interface with this module? All those sorts of things sort of keeps you from getting any more than one day out of sync with each other. And then you have resolution at the end of the day. So everything has to kind of come together. It has to be compilable. It has to fit together. It doesn't have to necessarily run right. But at least you keep things from drifting too far by using these methods. And you can use these in different size teams. But by keeping it small and testable, it keeps things moving very quickly. And you see agile methods are meant to do exactly what you would think the name implies, which is get software out really, really fast. So it tends to apply to some of the smaller development projects. It doesn't apply to everything. You look at large, million lines of code types of systems that are not uncommon in government. Be very hard to apply agile methods, at least to the whole thing. You might do it to parts of it. But I just wanted you to at least know about agile methods. So if you hear the term, you at least know what they're talking about. Now, we're going to talk about software metrics a little bit as a counterpart to the development models. Now, these can be very difficult to devise, use, and understand. And one of the biggest problems we have as technical people is getting non-technical managers to understand what we're talking about. For example, they want to know things like what percent complete are you? And that's really not an accurate way to estimate software development. It's not really compatible with time and effort to complete. Those words are all ambiguous. We'll talk when we get into architecture about something called the mythical man month, which talks about adding people and resources can slow the effort. So someone can say, hey, I'm 80% done and I'm scheduled to take 3 weeks to finish this last piece. And I have 4 programmers. And someone could say, well, if I give you 8 programmers, can you get it done in a week and a half? And the answer is most often, no. Not only will I not get it done in a week and a half, it's now going to take me 7 weeks or 8 weeks to get this thing done. So adding resources can slow the process. That's been documented time and time again. But the goals of requirements are to monitor, the goals of metrics are to monitor requirements, to predict what development resources you're going to need, how many computers you're going to need, how many programmers you're going to need, how many testers you're going to need, track progress because management does want to know how we're doing and when are we going to expect something to be done, and to understand the maintenance and supportability costs which are going to follow the development process. Now, when you think about how to use metrics, whatever you decide, they got to be understandable. So normal people can know what you're talking about. Don't use some crazy equation so that nobody can figure out how that equation matters to anybody. They should be economical. That is based back in dollars in some way. You should test them out. They should be timely, so you can do them on a regular basis. You should give incentives for process improvement, how you can do things better, and you might want to use them at multiple levels. Now, of course, the big question: what should I even be measuring? Quality is a tough one to measure, but size isn't. Lines of code has been used for years and years as a software metric. It is a notoriously bad metric because it encourages bad programming techniques. God forbid you should give programmers an incentive, a productivity incentive based on lines of code. You basically just told them to be very inefficient and take 5 lines of code to do anything a normal person would do in 1. Complexity, there are complexity measures for software. We can look at how complex the inner workings are between one module and another. How many entry points are there? You'll hear something called function points. That is the actual like methods in a class would be an example of function points. You might measure the requirements. You might measure the level of effort going into this. Maybe productivity as a factor of how much of these other things you're getting out for how much you're putting in. Cost is an obvious one. Schedule is an obvious one. How much scrap and rework are you doing? That's a good one that people don't think about. And then what about support? So here's some samples that you might just want to think about. They obviously don't apply to everything, but when you think about cost, plan versus actual, you can look at schedule, delivery dates, your percentage of how often are you on time, size we already talked about, the requirements, the total features that you're going to be delivering, the number of changes that you have to deal with. That's something will come up when we talk about architecture. We'll talk about that. No software product is what it is in the end, what it was intended to be at the beginning. So it's being modified as it's being developed. That's a problem because as the requirements change, you are adding complexity in the actual development of the product, which can actually push off the delivery date, which should actually push off the delivery date. So that's something we'll talk about in more detail later. There's tests. There's defects, right? The cost to fix, how many bugs are you coming across, the severity, how much workaround you have to do to what those bugs actually are. These are all things that you could be measuring. There's actually 3 types of software metrics. Management metrics that pretty much only managers care about. There's quality metrics. There's process metrics. Now, management metrics might fall into these categories where you're talking about indicators of progress against what the plan originally was. Impacts of change on the product process drivers. So looking at software requirements volatility, that is the volatility of software requirements on the implementation. the personnel status. These are all things that might be important to you at a management level. I'm thinking about quality metrics, software product attributes that impact the performance, user satisfaction. Does your customer like your product? How supportable is it? How easy is it to change things? So when you put your product out and your customer comes back and says, nice, but can I import these files? If it totally messes you up, that's not easy to change, versus it might be something as simple as writing a file loader. Technical measures might include something like reliability, usability, flexibility. You do understand that there's an entire field called software engineering that lives on this stuff. This is what that is an entire field of engineering, sort of a mix of engineering and computer science that talk about metrics and processes. So there's an entire field that's behind this. So I'm just giving you, again, a very, very high-level look at what exists that you can lean on, and don't feel like you're out on a limb. I have to come up with metrics for my program. What on earth will I use? It's been thought of before. There's a lot of precedent that you can rely on. And then, of course, there's the process metrics where we talk about software development management, the software engineering techniques you're using, the quality assurance process, and then we're going to talk a little bit about post-deployment software support. A few cautions on metrics. First of all, they're really indicators. They're not absolutes. No metric is going to give you such complete visibility into your software development project that you're going to know exactly where you're at and what the problems are and what you need to do to fix them. That's why we have lots of different metrics along the way. Be smart, have a plan, measure lots of things, but know what they're measuring. And the metrics are only as good as the data generated, which you got to be careful about when you apply these, because if your development team feels like they're spending lots of time producing data for you to manage them and not spending that time actually writing code and building your product, that's not going to go well for you. It's all got to be understandable, both to you, to your customer, and to the team that's developing, that's producing it. And metrics can't predict everything. You have direct comparison of programs should be avoided. So when you say, oh, I used this metric on my last project, I'm going to use it on this project, that may or may not be a good idea. Use your head, think it through. And of course, we already talked about this. Don't use a single metric. Now, this should look familiar to you. Think about that top bar that says concept, requirements, design and code, accept and install, operational. Gee, that looks an awful lot like the acquisition cycle. Not exactly all those words that we used, but some of them. And if we crack open the operational piece, we've got a life cycle of its own. You've got the initial launch. You've got the growth of the product. That is the adoption of the product into your market. And we're government, so I'm not saying that we're selling things, but when we produce a training system for the Marine Corps, there's a point of time in which the Marine Corps is getting used to it. We're getting it out there. We're training people up. They're starting to use it. Then there's maturity as it becomes a regular piece of what people use. And then there's a decline at the end as it's being displaced by the next cool thing that's gonna happen. So you should be used to this because we've been talking about this exact same cycle in lots of different modules in this course. Post-deployment software maintenance is what happens after you've done the whole development, and now this thing is out there, but you got to maintain it. So usually refer to this as just software maintenance. Some people may say software redevelopment. Here's the key here, what I want to get through to you, is that in some cases, as much as 60 to 80% of a program's software cost actually falls into this piece, which means that somewhere between 20 and 40% of your resources, of your overall resources in the entire life cycle of your program actually went into the design and implementation of the product. The rest of it is all in the tail. Now, that's interesting for the simple reason that this is where your legacy systems come from. Because what happens if you're the program manager and you end up out in the field managing this thing, and 60 to 80% of your annual budget is going into supporting the tail of these systems. And at the very same time, you're being pressured to replace it. How in the world are you going to replace this system when so much of your money is going into supporting the old thing when you really want to put that money into the new thing? So that topic is going to come up again when we talk about architecture and being smart about how we architect systems by cutting big things into little things, because we raise our probability of success and we give ourselves a chance at being able to deal with this legacy problem. So it's critical to successful post-deployment software maintenance. Determine the lifecycle support strategy early. Figure out what type of maintenance and support you're actually going to be able to support, you're going to be able to supply, given whatever resources you happen to have. So it's have a plan, execute the plan, modify the plan as you need to, but your goal is you want to get that 60 to 80% as low as you possibly can. That's your goal. And if you think about it up front, you can get it down pretty low. You don't have to spend that much money on the back end. And we're going to wrap up this module by just pointing you to some DoD standards. Lots of standards in software, software quality, software development. There's MIL standards, there's IEEE standards, which I'll show you next. Here's the IEEE standards. Remember what I said before. We're falling into the category here of software engineering, which is a discipline of its own. It's big. It's got a history. There's a lot there. You're not out on an island. There's lots of people that you can bring into your organization to help you with this. So you want to establish a common framework for your software life cycle processes. You'll get good at it. If you're going to be working in software, you are going to get good at this. You're going to find out what works and what doesn't. You'll be able to set up the metrics up front, and you'll have good processes, and you'll know which approach is best for which size project and what the characteristics of a software project are that require you to change your strategy. And that's all we're going to say about software development for the time being. But we are going to come back and touch on some of these topics again when we get to software architecture.